Okay, guys, just bear with me 1 second here.
Plugging in down there.
Okay, so I'm going to go ahead and just get into.
It's like the first day for burying like half the countries in the world.
I'm going to get into chapter 14. It's
Plugging it in.
the title is remedies. So just to look at the last few chapters. So chapter 12, we looked at costing energy. So we mainly looked at the costs of installing a system. We did a little bit of math and looked at the cost of doing the pumped hydro at Gordon Butte. 400 megawatts at $2 billion. Came in just above $2 a watt. Then in chapter 13, we looked at penalties and some of the pollution. And now chapter 14 says, well, let's turn the corner and look at remedies. And this book for 101 is very similar to the book for 102, and that when you take 102 in the spring, the last chapter looks at integration. So, and this chapter also looks at remedies across all energy sectors. So remember, in chapter 13, we looked at, really all of the penalties and the pollutions across, all non-renewables as well as some of the renewables. So anyway, so chapter 14 is remedies. And if we look right now, I'm just going to scan into this. This is a kind of a cool evolution, if you will, of different technologies and different problems. So if we look at 1900, urban smog was a big deal because people were still burning coal at home. In the 80s, acid rain was a big deal because we didn't have the proper scrubbers on our coal-fired power plants. Climate change is sort of coming online now. The ozone hole, to a large extent, I think has been amended. You hear news about the ozone hole kind of repairing itself as CFCs have been phased out. And now we're entering sort of this peak oil era. A lot of people will blame global conflicts on this. I'm not sure that happens. I don't know. It's like a door closing or something. So so here's some of the technologies. So you can sort of see the evolution of technologies. So there's candles, gas lights, very inefficient in terms of sort of their heat to light ratio. Incandescent lamps solve some of that. Fluorescent lamps come even further. And now compact fluorescence and LEDs, the majority of the energy is going into lighting. So this is kind of good news. Yeah?
This is trivial, but what does LED stand for?
It stands for light emitting diode. Light emitting diode. So a diode is an electronic device that only allows electricity to flow in one direction. And so it works just the opposite of a photo sensor. So in the solar cells behind you, photons come in and electrons get pushed out. In an LED, it's just the opposite. Electrons flow through and photons come out. So an LED is a PV panel in reverse.
That's kind of cool.
Yeah, it is kind of cool. Heating, so we went from wood, then on to coal. This is combined heat and power. So let's, instead of just exhausting all of that energy to the atmosphere, pump it underground. You see that in a lot of Scandinavian countries. Oh, and let's do a little insulation while we're at it. And then heat pumps are another kind of cool thing where if you have a large, remember, first law of thermodynamics, you can't create or destroy energy, you can just sort of move it or concentrate it. Then condensing gas boilers, a lot of times you'll see that even on residences. You used to see the big 6-inch, 4-inch pipe. Now it's just this little tiny 2-inch tube coming out. So a lot of that heat that would have gone off is now reclaimed. Communications, so we had electric telegraphs, telephone, radio, TV, now we're onto the internet, personal computers. This little blue line right here, if you're reading that paper that I wrote a year or two ago, you can sort of think of this as sort of that information line, the I dot, and maybe I'll even take a second to drive that point home. I think I started writing that. Writing that information and entropy paper in. Geez, I almost hate to admit it, but 2008. It took about 7 or 8 years to finally get. But let me just show you how. And then it really wasn't until teaching this course that those ideas started to coalesce and solidify. But let's just look. Here's the this red heating line. Maybe I'll just do that really quick. Pen, red. So here's that red heat. And you can sort of think of that as entropy, sort of disorder. And if you're reading that book, you're seeing the rate at which heat entropicizes the atmosphere. And if we come down here, telecommunications and computing, see if I can grab some blue here. Indigo, close enough. This is sort of the, info, communication, etc. That's information. So those two lines show the utility of both of these. And the idea for both and somewhere in between those two, I bring up this example, it comes up a lot. One example would just be the Nest system for your house. I don't know if you've seen those or not, but basically Nest is taking a delta T sort of between the outside of the house and the inside, and it's also doing some computation. So it's remembering what the weather patterns are. I don't know if it's sophisticated enough to actually see what kind of weather is coming in. The idea is it also knows if you're home or not, and sort of optimizes the whole system. And in my mind, we're sort of what we'd like to do in general is drive up efficiency. And what in my opinion, I think it's better if we sort of drive down entropy, so that we're not. And I liked your paper too, Rob. You showed toxins or
toxins release.
Yeah, toxins released in the environment. So in my opinion, that's another sort of entropization or pollution of the environment. So if we can sort of drive this entropy curve down, or just not drive it up as quickly, and drive this information curve up, that's where I see this sort of this confluence of better efficiency going forward. Less waste, better knowledge, better information, etc. So that's my interpretation of this figure.
Is that thing is that them knowing that you turn on the light in the bedroom, you're in that bedroom, or if you go under zone?
I don't think Nest the versions I've seen for Nest are just HVAC. It just runs your heating, cooling.
Because I've heard of
The most basic Nest program is, just for your heating and cooling, but then you can get other ones that are more advanced.
There are a lot of other technologies that are coming on to control your entire
That's what my friend
lighting
in the
system.
classroom, and he'll turn his TV on just as he can because it's on his
Yeah,
phone.
yeah.
I'm like, you're such an a-hole, dude. I wish I had TV.
No, you don't want TV. Okay, so here's oil-based transport. We talked. We spent chapters 4 and 6 talking about that. Electric traction, and what they've done here is just said, hey, look, the hybrid car is somewhere in between those two. So this graph is sort of it's a two-dimensional graph showing how these little technologies sort of pop up, and who knows what's going to happen out here in the future, but that's sort of something to consider. Is like, how do these different technologies combine and coalesce moving forward?
Yeah, finally have those flying cars.
A flying car, yeah, is going to maybe show up here somewhere.
Hoverboard.
Hoverboards. Okay, so coal plant for electricity. This is all stationary. Combined cycle gas turbines. Natural gas comes online. IGCC, I'm forgetting what that is, but CCS is carbon capture and sequestration. And already that's happening to a large extent. There's it's a 200-mile pipeline between Wyoming and Montana right now for carbon sequestration. The irony there is, CO2 is being pumped underground so that more liquid hydrocarbons can come back up. But anyway, here's uranium for electricity. And then here are renewables. So renewables really go all the way back, right? And you could, and most of this, some of it's stationary electricity, some of it is for transportation. Will we move on to this biomass, combined heat and power, hydrogen economy? So a lot of that we actually have right here. We've got this hydrogen fueling station that, if you take alternative fuels next fall, we can talk about that a little bit. We're working on setting that guy back up. So we do have a hydrogen fueling station here in Montana. There's a lot of interest now in biomass. Here in a little bit, we're going to talk about biochar, which seems to be this up-and-coming remedy for a lot of different things. I was even talking to someone yesterday who was just got back from Israel, and Israel is moving one of its military bases, and you got to do something with the dirt there, and because there's not a lot of real estate in Israel. So what do you do with it? Do you just wall it off and walk away? Well, no, they're using a lot of biochar as a remediator to soak up all these planes are coming and landing. So you've got brake fluid, you've got fuel that's in the soil, all these things. So anyway, biomass, combined heat and power, and hydrogen. I think I know we're moving in that direction. Okay, what is this? Looks like a big pile of sulfur.
I have rogue sulfur from Iceland that I got.
Oh yeah, you mentioned that. Mm-hmm.
That's cool.
Yeah.
Smuggle it across.
Yeah. So this is just a giant waste pile. Really, it's a sulfur removed from the Athabasca tar sands sitting on the quayside of Vancouver in Canada. And who knows though? One person's trash could be another person's treasure. Sulfur is used in making tires. We actually need sulfur in our diets to some extent. It's also used in some fertilizers. So depending on how you handle these waste products, they don't necessarily have to be toxic. But again, all of this requires some kind of energy, and this has obviously got there through some kind of conveyor belt system. That's why it's
crazy that they just pile it up next to the water like that.
well.
You know what I mean? Like,
Yeah, you'd think a little earthquake or some rain or what are the buggies? Well, I would hope somebody's
heads.
doing something good with it.
Like a little kid.
Yeah. It does say right here, today over 90% of world sulfur production is recovered from oil and gas. The fertilizer industry is a major consumer.
So it's not even natural sulfur?
Well,
It's just a byproduct then?
well, if you remember, let me just remind you where sulfur comes from. It's kind of wild.
Because I know it comes from volcanoes and stuff like that.
Let me show you here. Let's go to the
Because I know in South America, they have those guys walking in to double clean it and bring out chunks of it.
Sure. Well, and as with all elements on planet Earth, the going theory is that the all came from a supernova event, collapse of a star. But here you go. Check this out. So cysteine is one of the primary amino acids. There are 20 of them, and it's the one amino acid that contains a sulfur atom. So there it is right there. And the other kind of cool thing about sulfur, let me just show you. This is what allows life to do some kind of funky things. There's a couple cysteines in insulin. In my former life, I was a nanomechanics guy, so I know a little bit of this stuff. So sulfur sits right below oxygen, and if you look at the orbitals of sulfur, you can see that in that 3p shell, so oxygen has two missing electrons in the 2p, sulfur has two missing electrons in the 3p, and basically what that allows it to do is sort of have these two hands, if you will, to reach out and bind. Carbon's got the 4 fingers, hydrogen's got just the one little stick, but sulfur will form these, like in insulin, for example, a disulfide bridge, it's called, which allows the protein to take on sort of a loop-like shape for interacting. But that's where this, it's kind of strange to think about, but all of that fossil fuel life, all of those proteins in the plants and animals are now sitting there by the, yeah. But that's where they came from. They were assembled, with the nano machines of life, and then disassembled by the industries that run our civilization.
So these could possibly be the amino acids that were in the life.
Absolutely, yeah. These are the sulfur atoms that were in the amino acids that were.
They separate from the fossil fuels?
Cool. Yeah. Otherwise, it would have been the acid rain. It's sort of, and again, all these is kind of like pick your poison, and there it is, conservation of matter and energy. Yeah. Okay. So here's what we get ourselves into when we try to clean things up. They always become a little more complicated. Oh, and this is what I couldn't remember the acronym for, but it's Integrated Gasification Combined Cycle. So the idea is, rather than just go and set the coal on fire, and as strange as it is, as strange as it might sound, coal is not that easy to set on fire. We were doing this experiment, and you have to have like this giant propane torch to get the thing lit. It's like you need it's a little, it's not that easy to light a sparkler either. If the 4th of July, you don't just hold a little match out to it. The initial temperature has to be quite hot. But the idea here, instead of just setting the coal on fire, you gasify it first. So you heat it, and now all of the little carbon bonds, instead of being combusted, sort of just thermally shake apart. So that's basically what gasification is. Now you've got this sort of dirty syngas, if you will. Dirty just means you've got longer bonds in there. There's still some metals. There's all kinds of titanium and iron. There's a lot of sulfur, as we know, in coal. Dust and tar, so the bigger, so think of this as like a big cigarette filter, or cigarette butt, if you will. The gases come off, sulfur comes out. Now you've got the clean syngas, which is primarily carbon monoxide and hydrogen, and now you're going to burn that in the combined cycle gas turbine. So in the combined cycle, again, think of that as recovering more energy than you would if you just simply burned it. Here comes the electricity. Now you've got the flue gases, which are CO2, which is still the 800-pound gorilla or the elephant in the room or whatever you want to call it. Nitrogen and just plain old water. So this electricity then goes back to this air separation unit where you've got nitrogen coming off and sort of this pure oxygen. So it gets complicated, but that's the sort of the technological price we pay for cleaner coal, if you will. So when people say, what's clean coal? That's an example. But wait, it gets better. This figure's a little bit busy, so I'll just kind of read through it. Electricity generation plants with carbon capture. So if you remember that summary 2, this is sort of getting into the nuts and bolts of what's going on. So at the top, sort of the easiest to understand, it's the simplest. This is why you can see that, oh, it gets more expensive to be cleaner. So it used to be coal comes in, air comes out, electricity is the byproduct, flue gas, the SO comes off. This can now be used as drywall as a byproduct. The CO separation, and then the pure CO2 can go off to sequestration. But again, you're losing efficiency. Coal-fired oxy-fuel, this is kind of what we saw a second ago, where you have to have an air separation unit. And basically, the only separation unit that I know is where you actually have to cool air to the point that you reach the freezing, you reach the condensation temperature of oxygen and nitrogen, where you turn it from a gas into a liquid. They condense at different rates, and so you stratify them and pull them off. And then coal-fired pre-combustion. So here's what's called the shift reaction. So water actually comes in, and what you're doing is shifting the hydrogen and the oxygen molecules and going from CO onto CO2. Hydrogen comes out as well, and at the end, all of this CO2 is presumably going to go somewhere to sequestration, and we'll see techniques on that shortly. Hydrogen comes off, and then you can use that for transportation, perhaps electricity or other things. Then finally, this is why people say, well, let's just give up on coal. Look how complicated all this is. Let's go back to natural gas. Steam comes in, syngas, again, that shift reaction, CO2 and H2 come off, and now you can go through and actually burn hydrogen in a combined cycle, nitrogen and H2O come off. And so the idea is you've taken that carbon and blocked it in some way with oxygen. Well, in my opinion, the best thing to do with all it would just be to pump it into some greenhouses. Because as far as we can tell, and in fact, next week, I'm going to have a conversation with professor on main campus. His name's Frank Rosenzweig. I don't know if you guys, do you know him at all? If I'm not mistaken, Rosenzweig just got a really neat NASA grant to study exobiology. And whoever figures this problem out is really going to crack the big nut, if you will, because if you can send CO2 into a plant, into a living plant, and have it reassimilate that into its own structure in the absence of light, you've done it. Because right now, all the CO2 that gets pulled into plants, the lights have to be on, right? In the same way that in order for that solar panel, like the sun has to be shining.
Like the plant's respirating.
Yeah. So,
That's wild.
there's someone in a laboratory right now working on dark photosynthesis or a biology. And there's probably a mold or a mushroom or something out there that does it. But yeah, what? Go ahead.
I was going to say, are there types of plants that do that though, or they're called like nightshade plants?
There might
Or
be.
they grow at night.
Yeah, but what I'm not sure about is what the CO2.
Yeah.
Yeah, and I mean, if I were more of a botanist, I might know that, but here's sort of the, in each one of these outputs, there's the CO2, where is it going? Where's that CO2 heading off to? And well, feed it to the plants, of course, but how do you do that in a controlled, integrated fashion?
Because then you would be able to control like oxygen levels too, like you have to worry about the oxygen levels for human.
Well, yeah, I don't know.
Does it have to be like in like a trap?
Yeah,
Kind of like bubble.
I think the oxygen, I mean, the oxygen levels on Earth have been dropping steadily since the Industrial Revolution, but I think we're pretty robust. I mean, you can take,
Roll punches.
yeah, I think we've probably got a plus or minus 5% on the oxygen in terms of,
Okay.
yeah. All right, let's just take a little break, and I'll let you think about that. I just love thinking about the full cycle of these molecules.
Was